Hi, Assalamualaikum warahmatullahi wabarakatuh. So for this time around, me and my groupmate will be explaining about bending moment. These are my beloved members for the group. And so this is the overview of the lab report for this experiment. We have introduction, theory, experimental setup, until references and appendix. Now we shall go to the introduction part.
Alright, I will explaining about the introduction for bending of moment. So each of the beam are only held up by readily movable vertical support, allowing for different beam spans and support placement. A vertical bearing trapped in the mapping beam will be crossed by bearing in one beam at the cut portion. Display vertical movement for shear force monitoring free, while beam bending is allowed. The bearing and a tension spring that are supported horizontally from below the beam counteracted. The force of the load will cause the beam to bend and move vertically when it is responsible for these effects. The beams tends to shear due to the vertical displacement. The term shear force refers to the two internal forces present in the structural members at any given position, which are designed to prevent the load from moving relatively to the member in order to preserve balance. Every beam needs to be built with the ability to withstand bending moments and internal shear stress or shear force. The amount of load that a beam can support is a crucial factor in its design. Therefore, it is essential to ascertain the internal shear forces and bending moment distribution throughout the beam in order to build a beam for optimal efficiency. To determine the bending moment in a section, this is done by building a shear and bending moment diagram. Using the moment area approach, it is possible to estimate a beam's deflection with ease, as demonstrated by these two diagrams on the next slide. Apart from that, these diagrams make it simple to identify the kind, dimension and composition of a structural member, enabling the support of a certain set of loads without need for structural failure. This experiment successfully met its goal of determining the material's bending moment at a normal section when the beam was exposed to various loads.
For the theory of the bending moment, a bending moment is the internal forces that cause the beam to bend due to the external loading. A beam is a structural element that is intended to support heavy load from external sources as well as the structure itself. Bending a beam refers to the deflection of a beam from its present axis caused by an external load or structural load applied to the beam that is significant enough to cause the beam to shift from its original location. The bending moment is the result of the force applied to the beam and the distance between the force application point and the fixed end of the beam. Then, for the formula that has been used in this experiment, firstly, we use the formula of F times D to find the moment in this experiment. For the bending moment, we use the formula of W times A times L minus A over by L, which is equal also to M over by I, which is moment over by inertia.
So this is the experiment setup there's a load hanger labeled as P1, P2, and P3. The distance will be determined in the methodology, and then there's experimental beam load, which is we use 5 Newton, 10 Newton, and 20 Newton.
Then for the safety procedure, at the beginning of the experiment, we ensure all the equipment is safe to use. Then during the experiment, we handle and lift the load with caution to prevent any falls or injuries during the experiment. For the part 1 of the methodology, the beam has been set up and divided into 3 parts, which is P1, P2, and P3. The beam has been adjusted by using the spring balance until the liquid in the level is balanced. Then, The distance from P1 to P2 has been set up to 200 mm and point P2 to P3 is 250 mm. Then a load of 10 Newton has been added to P1. The spring balance has been adjusted again until the liquid in the level is balanced. The spring balance data has been recorded. Step 4 to step 5 has been repeated by replace the load of 10 Newton from P1 to P2 and replace again to P3. Step 2 until step 6 has been repeated with different type of load, which is 20 Newton load. Then for the part 2 of the methodology, the beam has been set up and divided into 3 parts, which is P1, P2 and P3. The distance of P1 and P3 from P2 was 200 mm and 250 mm respectively. The spring balance has been adjusted until the liquid in the level is balanced. Then the initial data of the spring balance has been recorded. The load of 5 Newton has been added to P2 while no load has been added to P1 and P3. The spring balance has been adjusted again until the level of the liquid is balanced. Then the data of the spring balance has been recorded. The step 3 until step 7 has been repeated by added the load of 10 Newton to P1 and P3 while the load at P2 remained 5 Newton. Basically, the difference between part 1 and part 2 of the methodology is the different type of load has been added to P1, P2 and P3, while the distance between the P1, P2 and P3 remain constant. Then, for the last part of the methodology, the beam has been set up and divided into 3 parts, which is P1, P2 and P3. The distance between P1 and P2 has been set up to 150 mm and P2 to P3 is 200 mm. The spring balance has been adjusted until the liquid in the level is balanced. Then the initial data of the spring balance has been recorded. The load of 5 Newton has been added to P2 while no load has been added to P1 and P3. The spring balance has been adjusted again until the level in the liquid is balanced. Then the data of the spring balance has been recorded. The step 3 until step 7 has been repeated by added the 10 Newton of load to P1 and P3 while the load at P2 remained 5 Newton. The difference between part 2 and part 3 of the methodology is the distance of P1 and P3 from the P2 respectively, while the load that has been using in the part 2 and part 3 is same.
Salam and hi everyone. So let's dive into a detailed explanation of the calculations and procedures involved in part 1, part 2 and part 3 of this experiment. For part 1, the initial phase, the experiment involved drawing and labeling relevant distances such as A to P1, P1 to P2 and P2 to P3. Table 1 provides balance readings measured by the spring balance, with all the readings registering as 0 Newton when no load is applied. As the load increases, the spring balance reading follows suit. The net force is determined by subtracting the balance reading at 10 Newton and 20 Newton from the reading at 0 Newton. The bending moment is then calculated by multiplying the net force with the constant value of RE to the spring balance, which is 150 mm. The theoretical value is obtained by summing the forces along the y-axis, and the first equation is derived by finding the moment at point B to determine RA. RA is then multiplied by the overall length, and the load is multiplied from P1 to point B. Additionally, RB is calculated to ensure the total value doesn't exceed the total force at the y-axis. And the theoretical value at point C, which is P2, is determined as it remains a constant in this experiment. The plotted graph illustrates the bending moment versus load, showcasing both experimental and theoretical values for P1, P2, and P3. Part 2 involves a change in the placement of the load but the calculations and the procedures largely mirror those of part 1. The graph plotted displays the bending moment against the load. In part 3, the load remains the same as in part 2, but the distances from P1 to P2 and P2 to P3 are altered. The calculations follow the same approach as in part 1 and part 2, with the only changes being the distances between the load and the respective points, and the graph illustrates the bending moment against the load. The percentage of error is computed using the formula. The modulus ensures that the value remains positive. This measure is applied to assess the accuracy of the experimental result compared to the theoretical values. This comprehensive calculation and analysis provide a detailed understanding of the experiment's methodology and the significance of the obtained results. The error percentage serves as a quantitative measure of the experiment's accuracy. In the discussion phase, Nadia will likely to elaborate further on the implications of the graph and the experimental outcome.
For the discussion part, which is part 1, graph part 1 was a graph of bending moment against load. As shown in the graph, the theoretical value of bending moment obtained was directly proportional to the load added. When the load is increased, it also increased the bending moment. Bending moment is said to be positive, which is sagging moment, at a section when it is acting in an anti-clockwise direction to the right, and negative, which is hogging moment when acting in clockwise direction. Graph in part 1 showed that the theoretical value of bending moment was directly proportional to the load, except for the theoretical P3. Theoretical value for P3 was inversely proportional, but when we did the experiment, the value was indeed positive. Hence, we calculated the percentage error for load 10 Newton and 20 Newton, and it was 117.87% and 115.64% respectively. The percentage of error were very large, and it obviously showed that there was some errors occur during the experiment. A negative bending moment in structural engineering usually happens when a beam stop is under compression and its bottom is in tension. It indicates that the beam is bending as a result of the forces acting upon it, creating compression at the top and tension at the bottom. Depending on the coordinate system selected and the bending direction, bending moments are traditionally assigned either positive or negative values. Understanding the structural behavior is important, then determining if a given moment is positive or negative. Next is the discussion for part 2 and part 3. For part 2, we use the same distance as part 1, which is 200 mm from P1 to P2 and 250 mm from P2 to P3, while the difference was the load added in each P position. As shown in the graph, the experimental line was slightly mirroring the theoretical line by chance. When we calculated the percentage error, we could see that the value is small and it may caused by some factors such as parallax error and the disturbance by the surroundings. Meanwhile, for part 3, the load hanging in each P position was the same as part 2, but we changed the distance to see if there any difference for the value of the bending moment. The distance used in part 3 was 150 mm from P1 to P2 and 200 mm from P2 to P3. Graph part 3 showed that the experimental line is more way linear than the theoretical. So, there were percentage error value because of that. The percentage error, after we calculated it, were 30.67% and 41.24% respectively. Hence, as a result, we could conclude that the closer the distance between P1 and P3 is to P2, the beam could bend with a higher value.
For the conclusion, the purpose of this experiment was to find the effect of applying various forces to the beam at various distance. From this experiment, we can see that the bending moment increased significantly with the increasing of the load. From this from the comparison of the experimental and theoretical values, there is difference in values that may be caused by the errors during the experiment. Since the percentage error is still acceptable, hence this experiment is considered successful. This is some reference that we use to write the report and complete this experiment.